In this video, we're going to go over some examples of what would be considered a standard basis for a set of vectors. So we'll try to do a little variety in here. So generally, the way that we create a standard basis is we allow what would normally be a variable to be 1, and then everything else in there would be a 0. So just a few examples of this. When we're dealing with a vector space that is R3, for example, a sort of generic looking vector within R3 would probably take the form x1, x2, x3, where x1, x2, and x3 can each represent any real number. So if we allow one of them to be 1 and everything else to be 0, we would wind up with one vector being 1, 0, 0, a second vector being 0, 1, 0, and a third vector being 0, 0, 1. In fact, with this in mind, these are so frequently used as standard basis vectors that they get special representations that are known as I hat, j hat, and k hat. Now this also lets us know that the dimension of this vector space would be equal to 3, because that's the number of vectors that we see in our basis. Now, that's true for any basis, not just a standard basis. For another example, if we wanted to consider the set of all polynomials of degree no more than 3. So, generic looking thing in here would be something like a constant term, a linear term, a quadratic term, and a cubic term. So a standard basis would be taking any of these coefficients, setting one of them to be equal to 1, and then have all of the rest of them be equal to 0. So if we were to do so, and I should probably do this using, actual notation, I could set a 0 equal to 1 and all of the others equal to 0. We would get 1 for that basis element. I could set a 1 equal to 1 and all of the others equal to 0 and get x as that element. I could set a 2 equal to 1, set all of the others equal to 0. And I could set a 3 equal to 1 and the others equal to 0. So I see in this standard basis for P3, we see a total of 4 vectors. So we can conclude that the dimension of the set of polynomials of degree no more than 3 would be equal to 4. Now, it's generally true that whatever number you see down here is going to be 1 less than whatever the dimension of that basis is. So again, now let's bump it up to the vector space being the set of, let's do 2 by 2 matrices. So a generic 2 by 2 matrix would probably be something along the lines of A is equal to A11, A12, A21, and A22. I could set any of those equal to 1 and set all of the others equal to 0. We would wind up with the following 4 standard basis elements. So setting the 1, 1 entry to 1 and all others equal to 0, we would get this. Setting A12 equal to 1 and all others equal to 0, we would get 0, 1, 0, 0. We could set A21 equal to 1 and set all of the other entries equal to 0. And we could set A22 equal to 1 and set all of the others equal to 0. Through this, it becomes rather easy to see that the dimension of the set of 2 by 2 matrices would be equal to 4 using these standard operations. Now that does take us to, what about subspaces or things of that nature? So with the 2 by 2 matrices in mind, something that we have discussed in class a couple times is the idea of the set of symmetric 2 by 2 matrices. So we'll define S to be the set of symmetric 2 by 2 matrices. So a nice generic looking element for something like that might be something like X, Y, Y, Z. Basically, for a symmetric 2 by 2 matrix, we need to make sure that the 1, 2 and 2, 1 entries are equal to one another. Now if I were to set one of those variables equal to 1 while setting the other two equal to 0, then the basis that I would get, the standard basis for the set of 2 by 2 symmetric matrices, would only contain 3 elements. It would be necessary that the second element has 2 1s in it. So it is as though we took the standard basis for the set of 2 by 2 matrices and combined these into one single matrix here. So the dimension of the set of symmetric 2 by 2 matrices would be equal to 3, since there are only 3 elements in the basis here.